All right, so phase two of amino acids is discussing ionization of amino acids. The first thing that needs to be known is that amino acids are alpha amino acids that we talk about in our biochemistry class, also known as proteinogenic because they're a part of protein. Um, they can contain at least two ionizable groups. They all contain at least two ionizable groups. Some of them contain three. Now, those two ionizable groups, they have their own pKa values and pKa's. The carboxylic acid has an acidic pKa, so you should think about this as being fairly low. And then the amino group has a basic pKa and will be protonated until you're at a basic or a higher pKa or pH. So whenever you see that, what's going to happen is the pH is going to go up to say something like 13 or something like that, and what's going to happen is that that amino group is going to become deprotonated. Now, this shows a rundown or basically a display. So what this is showing us is basically a look at different molecules and their pKa's and how those different molecules change based on an increase in a pH. So what we've got here is an acetic acid right here. Normal pKa for carboxylic acid or a carboxyl group is about 4.8. Methylamine has a pKa of about 10.6. Now what happens is that group is either protonated or deprotonated. So we've got at a lower pH, we've got our protonated form and we've got our deprotonated form. Likewise with the methylamine. The methylamine, well, that's going to be protonated at a lower pH and deprotonated at a higher pH. So these are all important things to look at and important to think about with respect to amino acids. So the ionization of amino acids at a low pH, the amino acid exists in a positively charged or a cation form. At a high pH, the there's a typo. The amino acid exists in a negatively charged or an anion state. Now between those, you have, or between the pKa for each group, the amino acid exists in its zwitterionic form. So that a Zwitter ion is an example of a molecule that has a positive and a negative charge simultaneously. Okay, so here is just an example of the amino acid glycine. We've got, and this is kind of important to, let's just start at the top here. Okay, at the top what we have is the cation form of glycine. Glycine, if you remember, has an alpha hydrogen and its R group is simply a hydrogen as well. Now, whenever that amino acid is fully protonated, that amino group has a positive charge. It has 3 hydrogens and a 4th bond going to our alpha carbon. Our carboxylic acid, well, that is also protonated at a low pH. And so that has no charge. So carboxylic acid has no charge and amino group has a positive charge. So overall, this molecule has a +1 charge. Now, you reach your zwitterionic form because the first pKa for this molecule is the pKa for our carboxylic acid. And that pKa happens to be, and you can see it in this graph right here, is 2.34, or pK1 is what it's identified as. The next pKa is for our amino termini, and that has a pKa of 9.60. Now, between those two, you have the molecule where there is an overall 0 charge. This is also, this is the zwitterionic form of the amino acid glycine, where you have a positive charge and a negative charge, and those are going to basically cancel one another out. That is known as the pi, or the isoelectric point. Now, being able to calculate that is fairly simple, and we'll get to that in a little while, but it's an important point to note. That is the point at which the molecule has an overall charge of 0. It also happens to be this zwitterionic form where you have both a positive and a negative positive group and a negative group on the same molecule. Now, amino acids are going to carry a net charge at our pi, that's what we were just talking about, a net charge of 0 at a specific pH. That is known as the pi. So in the case of glycine, it's fairly simple. You only have, or in the case of all diprotic amino acids, you only have two pKa values that you need to worry about. pK1, pK2, add them up, divide by 2, and you land at your isoelectric point. Now, what's important about this is that molecule, that amino acid, is least soluble in water when it is at its pi, when it's at its isoelectric point. Now, amino acids can also act as buffers because they have these different pKs. We've talked about pKs a little bit previously. You also talked about them in Chem 2. These different amino acids have two different pKa values, so they can act as a buffer, so they can maintain a pH at these two different points. In the case of glycine, well, it can use the carboxyl group, which has a pKa of 2.34, and the amino termini, which has a pKa of 9.6. So as buffers, whenever you have a solution with a pH of, let's say, 2.10 or something like that, and you've got a high concentration of glycine in there, and you add a small amount of a weak acid, well, that's going to be buffered with the help of glycine, and it's not going to cause that pH to change very much. It's going to be an effective buffer plus or minus 1 pH unit. So as buffers prevent change in pH close to the pKa, glycine can act as a buffer in two pH ranges. Now, this shows basically the graph that we looked at a little bit ago, and the shaded region is the buffering range. So we've got 2.34 all the way up to 3.34 and all the way down to 1.34, the ranges at which glycine can function as a buffer. And then, because of the amino termini, it can also act as a buffer as high as 10.60 and 8.60. All right, so that's the value that an amino acid has, or that's one of the values that an amino acid has. Ionizable side chains also have pKa's and can act as buffers as well. These ionizable side chains influence the pi of an amino acid. Ionizable side chains can also be titrated. Titration curves are now more complex as the pKa has more than, or it has one additional, the titration curve is more complex because you have that third pKa value whenever your side chain is ionizable. So if you look at something like this is histidine. Histidine has, and we're adding a little bit here, histidine in its fully protonated state. We've got the amino termini, we've got our C termini that's protonated, and then we have our R group that is also protonated. So the C termini has no charge. The N termini is +1, the R group is +1, so we're looking at a molecule with an overall +2 charge. Well, as you add base to increase that pH, you're slowly but surely titrating away the hydrogen ions that are on that C termini. So you're converting that C termini from neutral to being -1, in which case now you've got -1, +1, +1, so that's two pluses or two positives and one negative, meaning that your overall charge is +1. Finally, when you get to deprotonating that that R group, well, you're taking that from +1 to 0, and so now what you've got is you've got a C termini with a minus charge, an N termini with a +1, and an R group with no charge whatsoever. So that positive of the N termini and the negative of the C termini, those will effectively cancel one another out, giving you 0 overall charge. And then finally, the last display of this is, in the last place that you can remove a proton, is from that N termini. So you've removed it from the C, then you removed it from the R group, which gave you 0 charge, and finally you remove it from the N termini, which gives you a 0. So now you're looking at a molecule with a -1 overall charge. Now, here we've got our titration curve. This shows all of those values. The pK1 is 1.82, pKr or the pKa for our R group is 6.0, and then the pKa for our N termini is 9.17. Now, in order to actually calculate the pK or the pi for this, at what pH does this molecule have no charge whatsoever? What you need to do is you need to figure out what are the pKa values that show your transition from +1 to 0 and from 0 to -1. You actually don't even care about this first pKa. To calculate a pi, you are going to use two different pKa values, and you're going to divide them, or you're going to add them up and divide them by 2. Now, in this case, it happens to be the R value and the N termini's pKa value. That's not always the case in a triprotic amino acid. What's most important about this is that you understand and appreciate we are trying to find where this molecule has, or what pH that this molecule has, oopsies, that's supposed to be a straight line, has an overall charge of 0, and that happens to be at a pH of 7.9 or 7.59. So if you got a lot of histidine and you adjust the pH to 7.59, all of that histidine, chances are strong that it's going to precipitate out of there because, well, that's the point at which that molecule is least soluble. Now, let me just tell you that calculating PIs and understanding these titration curves is not really trivial. It's been at least a year since you took Gen Chem 2, so you might have to go through these a couple of times, but you'll get there, I assure you. Okay, so how to calculate the PI? We just did this, but we did it in a little bit of a faster way. In the case of histidine, what we did was we took the pKr, or the pKa of the R group, we added that to the pKa of the N termini, and we divided by 2. So that's what we got. And basically, that's all there is to calculating, looking at titration curves for amino acids and calculating PIs.